Okay, welcome to the lecture for research methods. We'll begin our discussion of how to design the method of an experimental study with this lecture on the distinction between internal and external validity. Once we understand what these terms mean, we'll discuss how different design choices impact each of them, and finally we'll discuss what things to consider when making those choices. Okay, so starting off with defining internal and external validity. Internal validity is about the degree to which you are confident that differences or changes in the dependent variable are attributable only to the manipulation of the independent variable. Basically, it's the confidence you have in the cause-effect relationship that you're examining. External validity, however, is about the degree to which a study's finding about that relationship between variables provides meaningful information about the relationship between those variables in the real world. So it's not just about generalizability in terms of generalizing other people. It's about generalizing statements about that relationship that you found in one setting to other settings and other individuals. Okay, so in terms of what determines internal validity, in terms of design choices, well, the first thing obviously would be the manipulation of an independent variable, which is one of the key features of an experiment. The second one would be measurement of the dependent variable, the thing that you're going to affect. Third, whether or not your groups that are created are equivalent. And last, the degree of experimental control. So we'll look at these four things in turn. Starting off with the first of the four, manipulation of the independent variable. So hopefully most of you know what an independent variable is. For those who don't, a quick review. It's the variable that you think has some causative influence over another variable. So it's the cause and the cause-effect relationship. It's also the variable that the experimenter manipulates. And, the experimenter determines what level of the independent variable a participant will experience or receive. Okay. And there are different ways to manipulate an independent variable, but basically you're either going to present different stimuli to different participants depending on what level of the independent variable they get, and that stimuli broadly defined. It could be showing some pictures, it could be experiencing different types of therapy, it could be receiving electric shock versus a not shock, something different happening to them, or it could be varying the instructions given to different participants. So in the first part of what I talked about how the independent variable, the experimenter controls what level of the IV participants receive or experience. So you're going to think, well, what does he mean by levels? Well, an independent variable must have at least two levels. There must be at least two different values for this variable. Frequently, the two levels or two values involve either the presence or the absence of some intervention or stimulus. So if you're doing a drug study, pill versus placebo. So, drug or intervention is the independent variable, and the two levels are you get the real pill or you get the placebo. Those are the two levels of the same variable. For therapy studies, it could be you get therapy or you're on a wait list, and those are the two levels of the independent variable. The independent variable is, again, some intervention. You can also have multiple levels. You have to have at least two, but it couldn't be more than two. So let's say you're looking at therapy. You could look at type of therapy as your variable, and then your levels could be cognitive behavioral therapy, gestalt therapy, client-centered therapy, and no therapy or wait list. And it just depends on what your question is, how many levels you're going to want to look at. Okay, so you're going to manipulate an independent variable, and you're going to choose how you manipulate it. And that choice will affect internal validity. But you have to have an independent variable to have any kind of internal validity. If you don't manipulate the independent variable, and that's a choice you can make, you're going to lose some internal validity. But sometimes the experimenter doesn't really have control over the independent variable. It's generally whenever you can't ethically or just practically manipulate the IV, because you're looking at something where there's pre-existing groups already happening. When that happens, instead of using an experimental design, you're still maybe looking at group differences, and you're kind of interested in cause and effect, but you don't have the power to assign people to conditions. You're probably doing a quasi-experimental design. In a quasi-experimental design, you have naturally occurring groups where the experimenter didn't assign people to a level of the IV. For example, if you want to look at the effects of divorce on depressive symptoms, you can't manipulate marital status. You can't make some people be divorced and other people not be divorced. Right? But you can find divorced people and married people and compare them. But if you find a difference in depression level between divorced and currently married individuals, you can't be confident that that the divorce caused the depression. It could be that it worked the other way, right? That maybe depression caused the divorce. Or people who are suffering from depression are greater risk for divorce because of the strain it puts on the relationship. So again, you lose that confidence in the cause-effect relationship, by which variable causes the other, and that there's maybe not even some intervening third variable. But still a valid design when you don't have any other choice. But generally, to do a true experiment, you have to manipulate the independent variable, and sometimes it's important to conduct something we call a manipulation check. So sometimes it's important to test whether or not you're effectively manipulating the independent variable. And this typically occurs when your manipulation of the IV is done through varying some stimuli that the participants are going to make some judgment about. For example, if you wanted to look at the effects of school affiliation on attractiveness, on ratings of attractiveness, you could show participants pictures of some person wearing a sweatshirt that said either TAMUCT or UMHB on it. Right? So trying to indicate that they're affiliated with TAMUCT or UMHB. But it's possible when people are rating the person in the picture, rating their attractiveness, they didn't even notice the sweatshirt, or they don't assume that the person's affiliated with the university just because they're wearing the shirt. So you can do a manipulation check, and frequently you do it in the context of a pilot study. And a pilot study is just a small-scale study that you conduct to help inform the design of a larger-scale study. So smaller group of people, and you're not looking at really the effect of IV, DV. You're just trying to figure out some things methodologically before you invest a lot of time and money and energy in your large-scale study. So kind of seeing if things are going to work right. So a pilot study, a test run. And one use of the pilot study, as I said, is to conduct a manipulation check. For the example we just talked about, you could ask individuals, after they've looked at the picture, so they look at the picture, you take it away, and we want to do a manipulation check, so we ask them, okay, what was the individual in the picture you just looked at? What were they wearing? So see if they can report, oh, they're wearing a sweatshirt, or they're wearing a sweatshirt with TAMUCT on it or UMHB on it. And then we might also ask them, if you had to guess, where this person was going to school, what would you guess? And if they notice the sweatshirt and they think they're affiliated with the school, then we are effectively manipulating the IV. If they don't, a large number of people don't answer those things, then we're not effectively manipulating the IV because they're not noticing the things we want them to notice. Okay. Okay, now the second thing that will affect internal validity is how you measure the dependent variable. And so a quick review, what is the dependent variable? Well, that's the variable you think will be affected by the independent variable. So the value, in your kind of conceptualization, the value of the dependent variable for a participant will depend on what level of the independent variable that participant received or experienced. Okay? So this is the variable that is kind of the effect in the cause-effect relationship. And in terms of what you do, it's the variable that's measured, not manipulated. Okay. Now in terms of how it affects internal validity, how it affects the confidence you have in the relation between the two variables, it's all about valid measurement, which our next lecture will focus entirely on this aspect because there's a great deal to talk about regarding measurement validity, so we kind of split that off into a whole separate lecture, to kind of give you a heads up that it's important and it affects internal validity, but it's too much to talk about in the context of this lecture. Okay, so the third thing that will influence internal validity is the extent to which you have equivalent groups. What groups are you talking about, you might ask? Well, your groups are comprised of participants who experience or receive different levels of the independent variable. For example, in a kind of straightforward treatment study, you may have the treatment group and the control group. Right? So if type of treatment is your independent variable, and one level is the active treatment, and another level is the control group, some inactive treatment, then depending on what people receive, if they get treatment or don't get treatment, they're in a group. So everybody that gets treatment is in the treatment group. So that's the group we're talking about. Obviously, this creation of equivalent groups is linked to manipulation of the independent variable. Basically, you want a participant who receives one level of the independent variable to be as similar as possible to a participant who receives another level of the independent variable. So you get treatment, A gets treatment, B doesn't get treatment. And A and B are they're as like as possible. Then, after we introduce the independent variable, so we give one treatment and we don't give the other treatment, then we do that and then we measure the DV. Then, if these two participants are different on the dependent variable after they've experienced or received the independent variable, then we can be more confident that this difference is due to the independent variable and not some pre-existing difference. The most common way to achieve this is to use random assignment. Now note, this is not the same thing as random sampling. We'll talk about random sampling in a future lecture. But basically, with random assignment, you start off with some entire sample, and you have one group. And you may have gotten that sample through random sampling or not through random sampling. Doesn't matter. Somehow you have a group. And then we're going to use random assignment after we have our sample. So the sample's established, and then I'm going to randomly assign members of that sample to one level or the other of the independent variable. And the assumption here is that the groups will be equivalent because any kind of random things going on with individual participants will be evenly distributed across groups. For example, if you're doing a study looking at a drug to treat depression, you probably will have some very depressed and some mildly depressed individuals in the total sample. Right? And the assumption is that random assignment will lead to a roughly equal number of very depressed individuals, participants, in each group, and roughly equal numbers of mildly depressed individuals in each group. So the groups will look similar. And this is just an assumption. It's what should happen based on probability theory if you have a large enough sample, but it may not happen, right? Because again, it's just ultimately random assignment probably creates equivalent groups. So if there's some variable where you think, well, it's really important that the two groups are equal on this thing, so maybe it's pre-existing depression, then you might want to measure that before you introduce the independent variable. So before they get treatment or don't get treatment, before they get the drug or get the placebo, measure the depression and see if the groups are equivalent. If they're not, then you've got a problem with internal validity. You may want to change some things around. But if you do have equivalent groups, then you can kind of move forward more confidently. Another approach would be to use paired groups design to achieve equivalency. And there are at least three ways to do this. One of the most straightforward would be kind of a pre-post design. Right? So your groups, in this case like two groups, if it's just time 1, time 2, are the same people. Right? Just measured before and after the independent variable. In this way, each person serves as his or her own control. So statistically, you're not comparing one group's mean to another group's mean. You're comparing each individual's score to his or her own score before and after the treatment and calculating that difference. You can also take kind of a more active step toward creating equivalent groups by, again, kind of measuring them on some important variable. So we talked about that before. We can measure them and see if the groups are equal. Or before we create the group, before we assign people to groups, we measure them on this important variable. And then we create kind of pairs of participants or groups of participants who score at the same level on this important variable, and then randomly assign half of the pair, half of the group, there's more than 2 people, to one level of the IV, and the other half to another level of the IV. For example, maybe you're testing some new method of teaching, and you want to see its effect on memorization, on participants' ability to memorize things. So you might think, well, intelligence might affect memorization, but that's not what I'm looking at. I'm looking at this teaching method. But I want people to be roughly equivalent IQ in my two groups. So you might test everyone's IQ, and say you have 20 individuals who score above 130 on an IQ test. Randomly assign half of them to get the method of teaching, the new method of teaching, and the other half to get no teaching or some other method. And you have another 20 individuals who score between 115 and 130, and again, randomly assign half to one group, half to the other group, and so on and so forth until you've accounted for all of your participants. And what happens then, you've made sure that your groups are roughly equivalent on at least one important variable. Another thing that you may see is when you have naturally occurring pairs. and sometimes naturally occurring pairs lend themselves to examination. And the best example would be identical twins. If you want people who are genetically similar in two groups, then you can randomly assign one twin to get one level of independent variable, and the other twin to get the other level of independent variable, and you'll be comparing each twin to his or her own twin, just kind of like you would with a pre-post design. So if you do these things, then you'll be avoiding hopefully selection bias. If you don't use one of these methods or some other method, you may be introducing selection bias, which reduces internal validity. An example of one way to introduce selection bias, which you don't want, obviously, would be if you let people choose what condition they wanted to be in. So let's say you're doing a smoking cessation study, and you let people choose if they want to be in the treatment group or the control group. Well, you're probably going to find the treatment group is more successful at quitting smoking, right? But it may not be because the treatment is so great. It may just be because those people are more motivated to quit. That's why they chose the treatment group. People who aren't ready to quit choose the control group, and maybe you're giving out, some incentive to participate. Like, well, I'll take the $5, but I still don't have to quit smoking, and they don't quit smoking. So you don't let people choose which group they're going to be in, and you're also careful about when you're creating your groups, not sampling from one location for one level of the independent variable and then sampling from another location for the other level of the independent variable, because now you've created a difference between the groups other than the independent variable. Okay, the fourth thing that influences internal validity would be the degree of experimental control that you exert. And experimental control is kind of a general term that refers to kind of all other efforts that are made to ensure that the experiences of participants at different levels of the independent variable, so treatment and control, are as similar as possible except for the independent variable. So not only are your groups equivalent before the IV is introduced, but they're treated equivalently during the experiment. There's two major categories of ways to address this. One would be eliminating confounds, and the second is reducing the impact of nuisance variables. In terms of eliminating confounds, what is a confound, you may ask? Well, a confound or a confound variable is a variable that is a systematic difference across groups, across levels of the independent variable, other than the independent variable itself. So if anything is affecting the treatment group and the control group differently, other than the treatment, then that's a confound. And it will lead to false conclusions along the lines of having you conclude the independent variable had an effect when maybe it did not have an effect. Because the groups really only differed because of this confound variable and not your independent variable, but they still differed. So you look like you found an effect, but it wasn't the one you were looking for. Some examples. One would be selection bias, which we've already talked about in terms of other things that influence internal validity in terms of creating groups. But there are also things like procedural differences, where you're kind of different things happen to them differently. So maybe you're testing the effect of teaching method of memory, I talked about before. In one group, the one with the new method gets tested in the morning, and the other gets tested in the afternoon. That time of day difference alone might be a confound. Maybe people, if time of day affects memory, so if that variable has a systematic relationship to the dependent variable, it's a confound. Maybe people do better memory tests in the morning than they do in the afternoon. Or maybe the air conditioning was broken in the afternoon and not in the morning. So people were uncomfortable, so they performed more poorly on the memorization test. So again, anything that can affect the DV that's different across groups, that happens differently or that you do differently, would be a confound variable. Another type of confound kind of related to procedural differences would be demand characteristics. This one, some part of the method leads participants to form an opinion about what's expected or what's happening, and then this opinion of theirs influences their behavior. For example, in drug studies, when you have the placebo versus the real drug, if you're having side effects, then that's kind of a demand characteristic. Because if you have side effects, you think, oh, I'm probably in the drug group, and so this may lead you to believe you're going to get better, which might make you get better, or might make you report you're getting better. And if you don't have side effects, then you might figure out, okay, I'm probably in the placebo group, I'm not supposed to get better, so no, I'm not feeling any better, right? So those side effects might end up being a demand characteristic. Another example, experimenter bias. This is when you subtly treat the groups differently. Smiling at one group and frowning at another. We're not exactly sure how we do this sometimes, but we know we do from some fairly clever studies. There's one study that was done a while back looking at the possibility of experimenter bias and the kind of expectancy effects, where some experimenters got a bunch of genetically identical mice, right, a bunch of clones of each other, and they arbitrarily divided them up into groups, and then sent them out to a couple different universities, and in kind of two separate shipments to each university, and labeled one group the smart rats and the other group the dumb rats, right? And then told them, okay, we want you to see if there's a difference in these groups in terms of how well they run this maze. And at every university they sent them to, the people running the experiment found the smart rats ran the maze faster. They learned faster. But they weren't really smart rats. They just had told them they were smart rats. And we don't know exactly what they did to make it look like they ran faster, but it sure looked like they ran faster. So experiment bias can have a very subtle and insidious effect of attacking internal validity. So one way to address this would be to use a blind, where the people running the experiment don't know what's supposed to happen. So they don't know what condition, what level of the IV somebody's in, or they don't know what the hypothesis is. And when you do that, it can help eliminate experimenter bias. Another potential problem is attrition. It can affect you in two ways. One, let's say you're studying one group over time, and basically you're looking at the effects of time or age. Right? So that's your basically quasi-independent variable. And let's say you're doing this long-term study, longitudinal study, and some people drop out of the study along the way. Now, when you're comparing time 1 and maybe time 4 data, it may look different, not because the people changed from time 1 to time 4, but because some of the people are now gone. A second way this can affect you would be if you're looking at two groups over time. So maybe you're looking at the effects of some variable over time. So really you have two independent variables now, or maybe one true independent variable, treatment versus no treatment, and another quasi-independent variable being time. And if you have differential attrition, right, then you're basically back to selection bias, because it's possible that people in the treatment group who the treatment wasn't working for dropped out. So maybe the control group nobody dropped out, or it could happen either way. But anyway, if you have a different number of people dropping out of one group or the other, you lose your equivalent groups, and you end up having kind of this created selection bias along the way due to attrition. A kind of related idea would be maturation, but instead of people dropping out, this is about how people change over time regardless of the impact of an independent variable. So if you do a longitudinal study and you have some variable that maybe you're giving, okay, I'm giving them 10 milligrams for this month, and then 20 milligrams this month, and then 30 milligrams this month, and you want to see how that changes their behavior over time, you need to have some control group that doesn't get a drug at time 1, time 2, time 3, because it might be over time people get better regardless of if you're increasing a dose or not. Okay. Another potential compound would be order effects. This is typically when you're talking about presenting stimuli, more than one stimulus to participants. So let's go to our example of having people rate the attractiveness of some individual based on school affiliation. So we're going to show them 3 pictures, one after the other, and it's always, here's a picture of a person wearing a TAMUC shirt, and then a UMHB shirt, and then a TC shirt. And a TC maybe is always the lowest rating of attractiveness. But it could be not because it had to do with Temple College, but because people get tired of rating over time, and so the ratings just kind of go down from A to B to C. In this case, order is confounded with school affiliation. So you can have fatigue effects, like we just talked about, where performance gets worse, or practice effects where performance gets better. So from first one to second one to third one, they're getting better at reporting or reporting more positively something. And the way to deal with this is by using a technique called counterbalancing, where you're presenting different orders of stimuli to different participants in a systematic methodological way. Okay, the other big area that we talk about under experimental control, other than eliminating confounds, would be to reduce the impact of nuisance variables. And we can't eliminate nuisance variables, but we can try to reduce their impact. So again, what are these? Well, they're basically variables other than the independent variable that affect the dependent variable, but they don't differ systematically across levels of the independent variable. So it's anything that affects your DV that's not your IV, but it doesn't affect one level any differently than it does the other. It affects everybody in kind of the same way. And this can also lead to false conclusions, but a different type of false conclusions than a confound. Remember, a confound will make you say there's a difference when there's not really a difference between your IV. Right? Nuisance variables tend to cloud the effects or obscure the effects of an independent variable because it's kind of like noise in the data. And in this case, when you have some nuisance variables that are unaccounted for, you're more likely to say that the independent variable did not have an effect when it might have really had an effect. It's just there was this other stuff going on where you couldn't see it. In terms of examples, like we talked about before regarding the testing of a new teaching method to enhance memory. Your intelligence level will likely affect the dependent variable, memory score, but it's not the variable of interest. So one way to deal with nuisance variables is to use matched random assignment, which we've already talked about. Another option is to use a statistical procedure to try to control for nuisance variables. So this is where you're basically using a nuisance variable as a covariant. And this procedure tries to approximate what the data would look like if everyone were equal on the nuisance variable. So if everyone were equal on intelligence, that would move your memory score up or down depending on where your intelligence is and what its relationship is with memory. And that's kind of a statistical thing. And you can't really control for intelligence, but that's a discussion for a graduate level stats class. But what I want you to kind of just remember in the back of your mind is, when you're reading articles, when you're writing your own paper, when people say, they've controlled for some pre-existing difference, statistically, that's not entirely accurate. You can't really control for it. You can attempt to control for it, and you're manipulating the data, but it's not the same thing as using matched random assignment, which is a better way of controlling for pre-existing differences. Okay. Okay, so that ends our discussion of determinants of internal validity. Now we'll look at external validity. What things determine the external validity? Well, first and foremost would be internal validity. And remember, external validity is the degree to which a study's findings about a relationship between variables provides meaningful information about that relationship in the real world. So, internal validity is necessary but not sufficient for external validity. If you're not confident about the truth of a relationship you're looking at within the context of your study, then it's not really feasible for the results of that study to provide any kind of meaningful information about anything in the real world. If you're not confident it's true in your own setting, then you can't externalize it, right? So you must have internal validity to have external validity. But then some other things will also influence it beyond that. The one large group being characteristics of the sample. So, is your sample representative of the population? Well, this depends on what population you want to generalize your findings to in terms of the degree of external validity. And this kind of highlights the fact that external validity is a relative term. It's relative to what information about the real world you're interested in. If you do a study looking at learning behavior in college students, and you're hoping to use the results to inform some decision about college students, then your study has good external validity for that purpose. Right? If you're interested in kind of creating policy about that would influence how all people learn, then your study may not have good external validity for that purpose. So, is your sample representative of the population which you are wanting to talk about, or which you think the things you're examining apply to? So it's not just the population; it's a particular population. Another thing to think about in terms of the sample is the size. And again, depending on your population, but generally, the closer the sample size is to the size of the population that you're wanting to generalize to, the greater the external validity. Right? If you had the whole population, then it would generalize probably much better than if you had one member of that population. Right? So bigger sample sizes generally lead to higher external validity. But beyond the sample, which is where most people kind of stop when thinking about external validity, because they think just about generalizability, but it really goes beyond that in terms of beyond characteristics of the sample to characteristics of the procedure. Things like the representativeness of the independent variable. Now, to what extent is the experience of the independent variable in your study representative of the individual's experience of this variable in the real world that you're wanting to talk about? So, how artificial or versus natural was the intervention? For example, if it's a study of some therapeutic intervention and participants receive therapy from an expert in that particular type of therapy, how likely is it that a typical client will receive the same type of care in the real world? Right? If it's this kind of unique therapy that only this one person can do, and then you say, okay, well, everybody in the world can get this therapy and it works, maybe not so much. Right? Related to that, representativeness of the dependent variable. I think we'll talk more about the dependent variable next time. But basically, to what extent does the procedure for measuring the dependent variable reflect meaningful changes or differences in a real-world context? For example, if you're looking at whether or not a drug is effective, an effective treatment for depression, and let's say we measure changes in depression, when participants draw a face. So we draw a face before we treat you, and then draw a face after we treat you. And some judges or judge evaluate whether the face looks happy or sad. That measure of depression might not really relate in a meaningful way to depression in the real world. So we'll talk about measurement validity in the next lecture. But so kind of a big picture, things that influence external validity. Internal validity being the biggest thing, and then it's all about to what extent do the people you're looking at and what they did, to what extent does that look like, to what extent does it apply to something in the real world that you're wanting to talk about. Okay, so this brings us to our discussion of internal validity versus external validity. Which is more important? Well, we've already said that internal validity is a prerequisite for external validity. However, it's also true that there's somewhat of an inverse relationship between the two. So frequently, efforts to increase one will lead to decreases in the other. For example, when you try to make your study less artificial and more like the real world, this frequently involves giving up experimental control. For example, if you wanted to observe people in their natural settings, it's much harder to assign people randomly to levels of an independent variable when just observing them in a natural setting. And you're giving up kind of a key component of internal validity when you do that, but you're gaining some external validity. So there's a tension there and a trade-off. Well, is external validity important then? Or maybe the question is, when is it important? Is it ever more important than internal validity? Well, how important external validity is depends on the goals of your research. If your goal is to generalize to some population, right? So if you want some type of maybe survey data that'll be used to make a policy decision, and it's important that the full constituency is represented, then yes, it's very important to have high external validity because you're going to be making decisions that affect everybody based on this one study. So if the study's impact is to be broad and have an effect on a lot of people, then yeah, it should sure as heck have some good external validity. But this is frequently not the case in our work. A lot of times our goal is to see if something can happen. So we want to know if a phenomenon can happen, even if it's under kind of artificial conditions, or maybe what conditions can happen under. For example, before we can figure out how to treat PTSD in the real world, it might be important to see if it's possible to treat PTSD at all. Now, we'll talk more about research and therapy later, but this is generally how research progresses in the clinical world. You figure out if a problem can be treated, and then you figure out how far you can deviate from these lab settings and still get significant results. Okay? Other times, our goal isn't again to make a statement about population based on a particular study, but it's to test a theory. So it's not to test if some findings will generalize, but if some generality, i.e. a theory, is true. And this goes back to the falsification approach, hypothesis testing we talked about before. if the theory says something should happen, well then it should happen in the lab, but in the lab you found it not to happen, then the theory is either false, or at least it's not always true, right? It's qualified. Which then leads, hopefully, you to think of the question, well, exactly what are we talking about the external validity of? And the authors of Chapter 5, and I tend to agree with them, suggest that we traditionally have the question a bit skewed, a bit off. And we should be examining not the external validity of findings of a study, but the external validity of theories. And so we ask, does a study provide a fair assessment of a theory, which we'll talk a lot about in terms of assessment later, but that has to do typically with your internal validity. So if we're testing the theory fairly, at least in some specific piece of the theory, and then to get external validity, we conduct multiple studies to determine for whom and when the theory holds true. So you don't try to get everybody in the world in your sample, because even if you get a representative population, let's say you get a representative sample, you get a representative sample, and to be representative, maybe there's some minority group that's 3% of the population, and so you have one person in your sample, and that's 3% of your sample. Do your findings really apply to that person? No. They may apply to the population as a whole, but you're saying, that person isn't that important because there's just one of them representing everybody in that group. So you're typically better off focusing on internal validity, in my opinion, in the opinion of some, focusing on internal validity and then conducting multiple studies with different people and different stimuli, different experiences, to then see to what extent some phenomenon, some theory might generalize. Okay? So, summing up, we talked about the determinants of internal validity, which include manipulation of an IV, measurement of the DV, which we'll talk about again next time, establishment of equivalent groups, frequently done through random assignment, and then experimental control, making sure people are treated as similarly as possible except for the independent variable. We talked about determinants of external validity, which involve both characteristics of the sample and characteristics of the procedure. And then we talked about how the importance of external validity really depends on the purpose of your research. So sometimes it's important, but not always. But again, internal validity is a prerequisite for external validity. All right? Take